Okay, so let's start with an idea. First data structure. Our first data structure of today is a linked list. And on a linked list, we were talking about arrays earlier, right? So just to re-review, an array, the constraint of an array is that you can have same data type and it's got a fixed length. I'm gonna write it down again because sometimes my length, there you go. Fixed length, same data type, and if you need to add one more element in an array, if you want to add one more element in an array, then you need to you need to create a new version or new elements. We need to add to create new array of size x plus 1. Fixed length, let's mark this as x, so that way it makes sense. So we're going to create a new array of size x plus 1 if we want to add a new element. Copy all values of other array. Add new value. And then delete other array. So in order for us to do that, to add more values, at some point from here to here, we have to double the memory that we're using. Once it's deleted, then it's recovered. So not only that, it's a lot of steps to do this, especially like when you have a really long array. It's an inconvenience. One extra restriction is that it has a continuous memory. That means that in order for an array to exist, you need to have can I see then on the thing, the full board? Yeah. Okay, you need to have whatever space is necessary that is all next to each other. So if you want to make a 1, 2, 3, 4, 5, 6, let's say a 5 array, but we have this memory in use, then we can't use these 3 cells plus these 2. We would have to use these 3 cells in order for us to be able to create an array of 5 elements, because this one is in use. So it's very limiting, but it's the initial way that computer scientists figured out how to represent a list of things. So then they looked at all these problems, and they were like, well, it's a pain in the neck to have to, how do I mute? It's a pain in the neck to have to do this. So why don't we figure out a new data structure where it doesn't matter how much free or available space you have. If, say, let me put it with blue, if these cells are in use, because that's what happens with computers. Sometimes memory becomes free or available. I can start inserting my list by going into pointers of what is the next available space for me. So let's say that the red ones here are the ones available for my list. The ones in blue are some other data type. And then when my list is done, I am pointing it to, this is the notation for null. So I know that my list is complete until I find a pointer to 0. So not only that, I can put whatever value I want inside of those elements, because a linked list would be something like, I don't know, let's say int value, or let's say it's a string. It's a list of names. It's a list of all your names. Okay? And then a pointer to another linked list object called next. And that's more or less like the data structure of a linked list. Meaning that if I have a node, it's going to store a value like, let's say Peter, and then it's going to have a pointer to the next item on the list. So let's say Sandra, okay? And then once the list is done, it points to null, and that's how you know that your list is done. The big disadvantage, as opposed to arrays, is that in an array, and let's assume that this is our array space, where the ones in red are our array elements, you can start by saying, okay, the array is pointing me to the first object, and I want to jump to the fifth element. All I have to do is add an offset and directly jump into that. In a linked list, because I don't know how many, well, I could count them, but that's part of like an implementation, but I would have to, in order for me to know where the next element is, I have to be following the links. So in order for me to go to the fifth element, I have to go, okay, where's the first step? Okay, the second, the third, the fourth, the fifth. Okay, this is where I'm supposed to go. But it's by visiting and then jumping around into each node. So in under that concept is a little bit less efficient, but you don't have to go through hoops and loops to add a new element, because when you want to add a new element, you just remove this pointer and add a new pointer of where it's going to go next. And same thing goes for removing. Removing, I just would grab, let's assume I want to remove this one, I remove the pointer to here, and then I point the pointer of the next element directly as where the result would be. So that's the concept of linked lists. And again, data structures is just the concept behind how we're organizing data on the computer. So there's special algorithms for like determining the complexity and things like that. But if we go then back to our slides, this is basically essentially what I was explaining about a linked list. So then let's go back actually into generics. Now that we understand a linked list and that you guys were assigned to this project where you are leading this project and you were writing the code of the linked list for the company that you work for. Let's assume that. So the CEO of the company comes in and he says, guess what? Our client loves the linked list. But they want to be able to do it with dates now. So that's easy, right? So your first idea would have been like, well, I'm just going to go on and grab the code of the linked list and make a copy. And now I am going to maybe save it in a file called date linked list. And now instead of I put the date as a value and the linked list element next, and now I have a new linked list. And then it goes fine. Let's assume that it goes fine for a couple months, and then they say, oh, the client really likes it. Really likes it. But now he wants to do a linked list of network sockets. And you're like, okay, well, am I gonna go again and copy the same file and search and replace? And well, we're at a time constraint, and then you make the bad decision of copying it and doing the same thing for the other one. Then 3 months go by, and then they tell you, oh, guess what? There's a bug and it needs to be patched for everything. And you're like, okay, well, let's go and find the bug where it is. You go, you troubleshoot your class, and you find it in the linked list original one. But then you go and maybe do it for the socket one, and you forgot about this guy. Now you have a bigger problem, right? Because you have duplication of code in 3 different places. So what would be a better alternative for changing this guy and this guy only, and not having to be reinventing the wheel or duplicating code? This is then where generics come to the rescue. Because generics allows us to, via Java notation, determine how we're going to do a live search and replace for elements. So anything that I'm putting, when I'm declaring the class, you probably inside of the API, you probably might have seen this less than, and then some value, and then greater than notation. And what that is going to say is that when you are creating an object, and just at that moment, it's going to do a search and replace inside the class and replace it with that data type. And it's only going to be valid for that instance only. So it's a live search and replace. Let's do an example so that way it's a little bit clearer. Okay? So now that we're here, let's just create, let's say, generics test. And we have created this class called generics test, and we're saying string value, just like we had on the linked list, right? And let's do public static void main. Let's make it public just so we can new generics test, and then we do g.value equals my name and then system.out. And actually let's do also okay, so we have a very simple class that has a string called value attached to it, and when we compile and run it, we're just getting my name, okay? What would happen if we did, say, replace me? And that becomes a new data type, exclusive to just this object. So now this replace me I'm putting it there. So when you don't pass anything, any object is available. But if I did generics test string and then string, this class is essentially doing a search and replace. Whenever you're doing generic test with that, is replacing that string. Just this guy here is replaced here, and anything that has the word replace me inside of the class gets replaced with that value. So it's essentially, if we go and write it in a very ghetto way, in here, and we say public class generic test, it's essentially doing public string value. That's the implementation after this thing is replacing that with string. Now, let me show you then what happens if I did this. What do you guys notice? It's an error, yes. And if I put my cursor here, what is it saying? Incompatible types, because it's expecting a string, because we're telling you that it's a string, but I am passing what? A date object. Now, if I change this to date, the error goes away. So essentially, I've made this class very versatile. And at runtime, I am able to replace those values. Who's following? Who's at 100? 100? 100? 80? What is it? 80. 80. Okay. I'll take 80. Okay. So, generics is a powerful tool. And now, when you go and say, if we go into the browser and we do Java API string, no, hash map. Oop. You can see, now you understand what does this mean. you now understand that notation. Because when you're going to create a hash map where K is going to replace anywhere where the key, the type of the key, it's going to maintain that object, and the value, the type of the map values. So now this notation makes sense to you, right? Okay, so let me just, okay, so let's talk about other data structures. I'm going to venture to say that this is probably the most important data structure in, come on. See it like this? Or can I control it? Yeah. Let's do it on this line. So the hash table, or in other languages it's called a dictionary, a hash map, has many names, but the concept is still the same. Okay, so there's one light concept I would like to introduce. Well, light. Let's make this hash map a little bit more complicated. Give me another name. Well, let's go. John. Actually, let's put the Beatles. Paul, George, and Ringo. Okay, so we added more elements to the linked list. And in a traditional concept, a linked list, and I'm going for a traditional concept. Of course, the people that write the built-in algorithms have added optimizations, and there's people that are very academic and very smart and have figured out better ways to do this. But from a traditional, strict linked list concept, if we wanted to find Ringo, we would have to go all through the elements of the linked list. If that's if we wanted to find Ringo. So in a list of n elements, our worst case scenario for finding that element, it would be that we would have to traverse n elements. In other words, let's replace it here. 1, 2, 3, 4, 5, 6. We have a list of 6 elements. In a list of 6 elements, the worst case scenario for me to find something is to do 6 jumps. And in a very, 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 very simple concept, on Java 3 we go more advanced on these concepts. We can say that the searching an element in its worst case scenario is of an order of magnitude of n elements. N elements is actually not too terrible, because if you chart time versus operations that you're doing, it's in a very linear way. So, you know, n elements is not the end of the world. Ideally, you want to start bringing it down so that way you can perform more operations per time. But in this case, the more elements on your list, the more time it will take you to find something. Okay? So there's this other concept that is probably like the most important data structure, because a lot of the times you don't necessarily always have to use one-dimensional list of elements. So there's this concept of key pair values where for each key is mapped to one specific value. So what that means is a key is a unique value that has only one answer. For example, capitals of the world. What's the capital of France? Paris. What's the capital of, let's see, Portugal? What's the capital of the UK? London. The US, Washington. So this is a nice list of key value pairs where you cannot have multiple capitals per country. So it's kind of like unique in a way. Yes. Oh, I thought you raised your hand. So these other data structure is actually very useful. It's called a hash map or a dictionary or a hash table. But basically, the concept of that is that it's a list or a series of key value pairs where each unique element is pointing to another element. Now, if you guys were to guess, if I wanted to find the capital of the United Kingdom, how many operations would I have to perform? And what I mean is by operations in the same list sense as the linked list. How many? You know already the answer. That's cheap. What would it be for you guys? What would be your guess?
You mean using the hash map or the linked?
The hash map. In a hash map, if I wanted to find the capital of the United Kingdom, you're just like, I know, I already know. It's okay, don't worry. I'm kidding about the cheat. If we wanted to find the capital of the United Kingdom, how many steps would we have? How many tasks would we have to perform? One. Why? The what? Yeah, but how would you? Why not go through the entire list? Is what? No, but so you have all these key pair values, right? Yeah. And you're trying to get to London as the answer. You know the UK.
Does it mean when you are looking for UK and they need to take a look the whole list?
Well, that's the logical answer, but that's not the real answer. He is correct and he is correct. It's only one operation, and let me explain to you why. The key of this is in the name of the data structure. It's called a hashing function. Basically, the way that it works internally is that it is going to have, I don't know, a hash value, and say, I don't know, could be also like another hash value and then a pointer to where it's going to go. The entire thing is, given a key, you apply a function to that key. And that is going to essentially tell you the location in the hash map where things are. Rather than having to scan the entire thing, when you apply a function to the key, it tells you where the value is. Which makes this data structure incredibly fast. And that's probably why it's the most important one. Because even for something like this, you could technically map all these as keys and an empty string as a value. And in order for you to find if Ringo is there, you just need to see if it's pointing to somewhere where it's got a valid memory location. And it expands beautifully automatically. And you know, in very simplified terms, it handles itself the off chance, depending on the hashing function, that the same key could point to two values. It handles it also on its own, which if a linked list was for searching an element of an order of magnitude n, for a hash table is a single operation. Any questions about that? I'm trying to do it like in the most simple terms. Like there's full papers about this written. But so the constraints are that the keys are unique. You cannot have two entries for the United States because the hashing function won't point into two different things. If you re-enter a value twice, then the latest is the one that is going to be held. Does that make sense? So for example, if I say that countries that actually have changed their capital, let's say Guatemala has changed their capital from Antigua to Guatemala City, they did change the capital. So you know, they essentially updated the entry on the hash map. Brazil did that too. When they went from Brasilia to Rio de Janeiro, they did the same thing. So there's no two capitals at that point. So so the keys are unique, and there's only one key per value, meaning you are just mapping one to one. Now, one thing about a hash table is that it's not ordered. There are some structures that are more advanced, like ordered hash maps and whatnot. But from the traditional concept of a hash table, it's not sorted in any way. Okay? Who is at 100 here? You're at 100 already. Who is at 80? Okay. Any questions that I can answer on this? You don't understand what?
I don't still understand exactly how we search it, like how we get to the.
Well, what I was just showing you is the internals of how it works. But let's do a code sample so that way you guys get to see it. Okay? Let's say hash map And you can see here that there's generic values. K and V have the notation. So either hash map or hash table is, basically the same principle. And let's say string. That means that the key will be a string, the value will be a string. And let's say world capitals. Okay? So we do world capitals dot put. I can just go and say, let's add Canada, Ottawa. Let's add Italy, Rome. Let's Japan, Tokyo. Let's put for Argentina. Okay, so we've got a few countries here where we've put the values, right? And in order for us then to get them, to search them, we can do get, and let's just look for US, which we haven't put the value of. But let's just, the value is null. And I can actually even check if world capitals dot contains key US, then I can look for the US, else system.out.print US is not found. So if I run this guy, because I didn't put the value for US, it's telling me US is not found. So I'm using the API, the key methods, put, contains key, and get for that purpose. Does that more or less make it a little bit more tangible?
Yeah.
Okay. So one exercise that I would like to do, so you guys get a little bit more familiar with it. On Java 1, and we're gonna do this together because otherwise it would be a little bit unfair. What would be a good one to read? Actually, a hash map is a great structure also for counting words, for example. And that's actually how Google works. So, word counting, let's go and find some lyrics. What would be a good one? A Day in the Life lyrics by the Beatles. So, this is not it. This line is not there on the song. I know this song in and out and they don't really have that line. Excuse me. This cough has been already 3 weeks with me. I think it's more like irritation from speaking. So I'm just creating a file and I'm just putting it there. Okay, so I've got my lyrics. So here I'm going to do public. File input stream. I say I think it is. Equals new buffered input stream, and we put that guy, and let's just import this. We'll just put everything right now on a try catch. This is not a desirable practice because if something, well, actually, why is wrapping everything on a try catch a bad practice? Anybody has a guess?
Is it because if you don't handle the exception or the correct type of the exception, it'll break?
Or it will fail silently, and you will have once you have a lot of code, you will have a super hard time trying to find out what is failing. A silent fail is probably worse than any fail. So right now I'm doing an exception here, but I say well, how was it to read the hang on, Java buff. I'm right now a little thinking about Python rather than buffer reader. That's why. Buffered. Read line. Yeah, there you go. So right now, it's required boolean. Let me just copy this. Okay, so I create a buffer reader so that way I can just read line by line of the file, and I am just printing it, okay? So I can read the file right now. So now that I can read the file, I can use a string tokenizer. Who has before heard about the string tokenizer? No? A string tokenizer, what it's going to do is that right now we're reading line by line each part of the code, and that's what we're printing. A string tokenizer is going to grab that line and break it down word by word. If you think it that way, we're breaking down the file into essentially an Excel file where each row is each line of the file, of the lyrics, and then each column is a space. So like we could put like, I read the news today. It's in one different cell. Okay, so we're gonna use a string tokenizer for breaking it down. What's the string tokenizer? And then actually we can do like something like while we're putting a while in this case. I'm not in love with it, but it's just like the quickest way. st system dot out dot print ln, and then we're going to do st next element. So it's for each line, for each word, we're going to go and print it in a new line. So if I read it now, I get that. Also at the very end, I'm getting an exception because it's a null pointer exception. So I should just assign it and say while, actually let's move this line of the line till the very end just to see. So now we have each word separated and just printing out like that, okay? Any questions so far of this code? No? Okay, let me make this a little bit bigger. Actually, no, let's just close that. Okay. And we're gonna put a hash table. Oh, hash map. String, comma, string. No, string, comma, integer. Word count equals new hash map. String, comma, integer. Why string, comma, integer, guys?
Word and count.
Because exactly a word and the counts that I've seen. So for each word, which is what I'm getting into this part, word equals string word is the next element. So what's the next token? So then I'm gonna check if we already have it in the word counter. And I'm going to use a get or default method. What that does is that either I get the word or I can get a 0, because if I don't find it, rather than getting a null, I want to get a 0. So I'm going to say integer value. I'm going to cast it into I probably didn't even need to cast it like that because it's if you see it this way, is using the return value is defined already by the hash map. Let me even show you that. Oh, here. Get or default, the value is v, and if you remember, we were using it as a generic as key v. So kv for us is string integer. Okay? So we have string and integer, so we're getting an integer, and if we don't find it, then we put a 0. We increment the value because we did find the word, and then we're going to do word count put. Actually, we can do something like this and remove one line. We're going to put the word back into the array, and then we say new integer. We have to put an object. That's why I'm using an integer. Like for generics, you always have to use objects. You cannot use primitives. Does that make sense? Can anybody understand the reason why we're not using primitives on that? The compiler only allows to replace objects. Just keep it as simple as possible. The compiler only allows objects. So if we're using this wrapper objects, do you guys remember that we talked that for every primitive, like int, there's an integer object. For char, there's string. For float, there's a float with a capital F. So there's like analogous object that is a wrapper around the primitive with a lot of convenience functions. So variable expected. Yeah. So far, who's confused about this? Everybody's okay? Okay. So then, at the end of the day, at the end of our reading of let's just print our word counter. So now we have that the word he appears twice, you appears two times, out is 2, found is 3 times. So if we go back into the lyrics, there it is, found 3 times. Found my way downstairs, found my coat, found my way upstairs. So the word counter is doing its work. The word the, it appears 12 times.
How does the string tokenizer handle like punctuation, like commas? Does it just remove it?
No, you would have to clean it. And there's some that here,
That's still considered like a word.
yeah. Yeah, so a string tokenizer is just a way of splitting a string via one character. But some of these, see, up, comma.
Yeah.
So if we wanted to like go further, we can clean the string a little bit better. But this is a way of understanding hash maps, I think, a little bit better. Any questions about this? Huh? Yeah, I just want to get both sides. Okay. All right, so now we are comfortable with the hash table. The next data structure that we're going to add to your vocabulary, it's a stack. Now, why am I going into data structures when some Java classes might not cover that? Could I, going back to the cooking metaphor, could I talk about preparing dishes without talking about flavors? In reality, both things are tied to each other. So the computer theory of all these things is also quite tied to the same, to programming, and also in a little bit I'm going to show you like some of these structures are already built in. But by teaching you about how these data structures work, you are learning the API, like some of the concepts of the API. So a stack. One, man, this had never given me problems before until today. Oh, you will need to replace that. Okay, so we've talked. No, I need the whiteboard. It was not like that, like last class or class before.
It just kind of gets finicky, when it's
Well, you just.
It usually gives me problems, so I'm surprised that it's working for me.
Oh. All right. Okay. Thank you. No, I don't want to mute. Okay. So now we have hash maps. We have linked list. What is the word stack? When you hear the word stack, what comes to your head? Who doesn't have a dishwasher? Okay, all of you have a dishwasher. Lucky you. In my day, when my mom wanted to teach us a lesson or two about cleaning the house, she would make us clean the dishes by hand. So obviously the most natural way of putting dishes is in a stack. So you have, your plates. Let's put another plate, and then another plate, and then another plate. So you have like that. Or who likes going to IHOP here? Who likes pancakes? Okay, pancakes. A stack of pancakes. The thing about a stack or a stack of coins, there's many real life examples of stacks. A stack of books, a stack of papers. The thing about stacks is that the way to read the data is that the last element that was put in is the first element to go out. Does that make sense? So if we had a stack of dishes and you were going to wash them, the last one that was put in, the one at the top, is the first one that you take out. So that's the rule number one. It's last in, first out. LIFO. And there's two operations that are related with a stack. One is push, which puts the element at the top, and the other one is pop. Right? So technically, you can't, like if you have something that is stacked and it's pretty heavy, you cannot just lift and take the one in the middle. You have to be processing each one of those. Now, the difference between the practicality of this data structure to this data structure, so this is linked list, and this is a hash map. On this one, the purpose of this one, on the linked list, the purpose of it was to overcome the challenges of an array, right? And the purpose of the hash map was to provide input and output that was fast. But in a stack, it's not really about making a data structure that makes things more efficient. In both of these cases, it's about efficiency. In both of these guys, we're talking about efficiency. And on this one, we're talking about utility. What's the difference between efficiency and utility? Any thoughts?
Utility is like you're using that data structure for a specific process.
Correct, it's for process. The other one is for utilizing the resources as efficient as possible. This one, doesn't matter if we make it like an order of magnitude, whatever. The fact that it's a last in, first out thing, you're always going to be bound by certain rules. So that's that's data structure number one. There's another data structure that is similar for the purposes of utility. And it's something that you guys do basically every single day in more ways than you can actually think. And it's called a queue or a line. And the line, as opposed to the stack, this is a stack. This is a stack. A queue is essentially something lined right behind the other. And that means that when you put something in the queue, the first one in is the first one out. So it's a FIFO. Very different than a LIFO from the stack. Again, it's utility. We're not really optimizing resources for efficiency. We're being bound by rules. So you go to the bank, the last one that went in is not going to be moved to the first, unless somebody has influence or an emergency or something, or they allow it to. But for the most part, the first person in is the first one that is attended, and everybody takes a number afterwards. You go to the market, and then they have a little number for helping you. You are even in a traffic light, it's a line. Everybody's queued up. Now, computer examples that use these two data structures internally. Stack. Who has heard of the website Stack Overflow? Well, Stack Overflow refers to filling up the stack and essentially causing a crash. That was a C error, or a program or an operating system error. When the memory was full, you would get a stack overflow. That means that you overflew the stack allocated for that program. So the memory works as a stack for creating objects. In a queue, now with the popularity of multitasking and distributed systems, there are certain processes, like for example, if you right now all went, and I highly encourage this, and went to your Facebook account and went to deactivate it, or and first obviously you want to download your files, it's a big process and it's going to take a lot longer than what your browser can actually wait. So it goes into a process queue, and they will shoot you an email once your data is ready. So sometimes whenever you're doing something online and they tell you, oh, you want to download this file, we'll send you an email when it's ready. It's because it's performing a heavy query on their database, and it's put in a queue so that way one by one they can take care of it. So right now in computing, queues have become a popular thing with systems like RabbitMQ or Redis or things like that. But that's a different topic. Again, these are for utility, these are for efficiency. Any questions? No? Okay. There's one extra data structure that I want to visit before we jump into doing like a couple of exercises. Actually, we've got to talk about lambda functions. There's another data structure that we've kind of talked about, but we never formalized it. There's been a point in our class where I've drawn something like this, and it was with what?
Inheritance.
It was with inheritance. And in genetics, this is called a family what? A family tree, right? Because if this was inheritance, this representation is called a family tree, right? Okay. But in reality, in a data structure, maybe I should just move a little bit. Is it visible? Yeah. In reality, this structure is called a tree. And what is a tree useful for? A tree is useful for a lot of things. There's even mechanisms of sorting lists that are facilitated and accelerated by translating a list into a tree and then back into a list. A mechanism, one of those would be a heap sort algorithm. So trees are, we think about trees in a lot of ways. There's this other concept called, for example, decision trees, that for each concept that you're trying to like map it to something, like if A, yes or no, well, yes or no, well, if A, then this, and you know, like you can map a decision all the way to, you know, a procedure, and basically a decision tree can be also translated into code for simple if-else statements. But the most common of all the trees is called a binary tree. That's kind of like and why would it be called a binary tree? What would it have to be so that it's binary?
Each node has at most 2 children.
Exactly. Each node has at most 2 children. That means that, you know, in some trees you can have like something like that, and that wouldn't be like a binary tree, because, you know. But in the case of a binary tree, there's multiple ways, like a red-black tree or other types of trees that allow you to find data quickly. Let's go into an example. So let's say that we have, and I'm going to copy the one from the slides. Let's assume that I have a 14, a 19, a 6, a 2, and then here it would be a 13, and then over here a 5. And then on this side we have a 19, a 16, 26. And this is kind of like how heap sorts work, you know, but where by rotating and rebalancing the tree, balancing the tree means that you would move nodes around to either to make sure that it's in a specific order. So 21, and then here we have a 30. Okay. Okay, let's try to find, according to this structure, this 3 is really ugly. If I wanted to find the number 30, how would you find it? Please go to the board and help me find number 30. Just mark it with a red.
So you mean market?
Correct. How do you determine that?
When we go this step, and is it greater than 6 and less than 19? And if it's larger than 19, and go this track.
Yes, correct. That's exactly the way. You saw how, by the way that she did it, that's exactly the way that it's done. By the way that she did it, we didn't have to visit all of these nodes. It's like, is 30 greater than 14? Yes, then we go into the right-hand side of the tree. Is 30 greater than 19? Yes. Is greater than 26? Yes. And we found it. So we only visited 4 nodes, as opposed to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we essentially cut. So out of 10, so we did 4 out of 10 nodes. We've essentially cut the amount of time or the amount of operations by using this data structure. So that's why it's really useful for sorting big things like that. So you can move it from a list, translate it to a tree, sort the entire thing, and then send it back. And it's gonna cut the amount of movements and operations. Make sense? So now we know how many data structures. We have a tree, binary tree, we have linked list, we have hash maps, we have stacks, and we have queues. Now, we've talked about the internals of, certain utilities of a linked list, just having a list that you don't have to be redoing like an array. A hash map we used as an example, a word counter. A stack we used a memory or like even processing certain things. Queue we used the like long running processes. What would be a good use for a tree?
It's a BST,
A BST?
binary search tree.
But what uses a binary search tree?
Search for elements efficiently.
If you're searching for something that you're thinking about, some computer concept that stores a lot of data, what would it be? Where do you store data in a sorted, in an organized way? Who's here taking the application certificate program? I think you are in the application certificate, right? Yeah, okay. Who is taking any database classes? Nobody yet? Okay, so you're taking database class. Okay. Database indices work this way. That's how database indices work internally. That's how everything is fast. Because you're cutting the amount of elements that you have to visit. So this part has been very theoretical. I think we should go then back into the concepts of lambda functions, and then before we go into a little bit of an exercise, because we're gonna run out of time. Who's at 100 so far? 100, 100, 100, 80, 100? Everybody's at 100. I'm doing my job. Okay.